Hello and welcome to video 11.1a for a discussion of significant figures. You have probably dealt with significant figures already. And so this video is certainly not meant to insult your intelligence. It is meant to help you review. And if you're new to significant figures, it's meant to help you understand and make sure we're all on the same page. Significant figures play a significant role in science measurements. First of all, a reminder about the difference between exact values and inexact values. Exact values, a dozen equals 12. The number 1 and the number 12 here have an infinite number of significant figures. 1,000 milliliters equals 1 liter. By definition, this is a conversion. This is a definition of a conversion. And since it is a definition of a conversion, this is an exact number. 1,000 is an exact number. 1 is an exact number. These have an infinite number of significant figures. But this definition of a conversion, 1 mole is 6.02 times 10 to the 23rd, is not an exact number because this number actually comes from measurements. And inexact numbers are essentially every measurement. The big idea is that all measurements have a limit of precision and accuracy, and this must be taken into account when evaluating experimental results. We'll talk about significant figures here. And I think I often get the question from students, why? Why do they matter? Well, they allow scientists to clearly communicate the precision and uncertainty of a measurement. On your calculator, the number 12 and the number 12.0 and the number 12.00 are all the same, but they represent different things. The number 12 here is 12.2, is it 11.9, 11.7, 12.152895. To two significant figures, this is 12, but the measurement only has that level of precision. Here, my measuring device maybe is a scale that goes 2 places past the decimal, and it read exactly 12.00. I say exactly 12.00, but I don't need any more zeros after that because the measuring device didn't give those to me. So even though our calculator says these are the same, they are not the same as measurements, and significant figures allow us to make that determination. So let's look at a few measurements and kind of give some context to significant figures and that whole phrase I just gave you. This is looking at a burette, and if you remember reading burettes from Chem 2 or your previous Chem class, if it wasn't with me, this would be 6.6, this would be 6.7, and this meniscus is somewhere between 6.6 and 6.7. So it's probably about 6.64 milliliters, plus or minus 0.05 milliliters. And this number 4 is an estimate. It is an uncertain number. And you might have got 6.63 or maybe 6.65, but it's clearly not down here near the 6.7. It's clearly closer to 6.6 or maybe right in the middle if you can read the bottom, the very bottom of the meniscus. And so I'm estimating this number. This uncertainty comes from the fact that the uncertainty will be half of the smallest interval. So that's important for us to remember as well. Here's a digital scale. All of these digits are significant, including this 0, because the balance is telling me that it was 125.30, not just 125.3. One last look at a graduated cylinder. Notice the interval is 0.1. The interval divided by 2 means my uncertainty is 0.05. And I think the bottom of this meniscus is somewhere between 6.3 and 6.4. I think probably 6.33. centimeters cubed plus or minus 0.05 centimeters cubed. This last number is an estimate. You might have said 6.62, you might have said 6.64, depending on how you read that. And quite frankly, when we zoom in this far, I mean, where is the mark for this line? Is it the top of this line or is it the bottom of this line? I'd say it's in the middle of the line. So I got 6.6, I got 6.33. What did you get? Now, in terms of significant figures, the number of significant figures in a measurement is the number of digits that are known with certainty plus the last one that is not absolutely certain. Think about the last example, 6.33 centimeters. Centimeters cubed. This 3 was uncertain. It was an estimate. And so we had our uncertainty of plus or minus 0.05. Even if you go back 2 slides to the mass, and that mass was 125.30, even this 0 is uncertain because that balance would have an uncertainty of plus or minus 0.01. So that last digit is not known with absolute certainty. Significant figures allow us to give that, like, how precise is our measurement, and with an uncertainty we can also know how uncertain, what is the range of that uncertainty. So there are simple rules for significant figures. If you are reading somebody else's measurement, there are simple rules for significant figures. First of all, any non-zero number in a measurement is significant. The number 5, the number 2, the number 8. So the number 6.33 has 3 significant figures. Zeros can be significant if they occur between numbers, like 502.21 grams. This 0 is significant. 6.02 times 10 to the 23rd, this 0 is significant. So this has 5 significant figures. This has 3 significant figures. Zeros can also be significant if they occur after a number and after the decimal. So 0.20 grams, this 0 is significant and has 2 significant figures as a measurement. 5.0, this 0 comes after the decimal and after a number, and so that means that this number as a measurement would have 2 significant figures. 0.0590, this 0 is after a number, and by after a number I mean after a non-zero number. It's after a number after the decimal, and so this has 3 significant figures. These zeros are not significant, and they're not significant because they are simply placeholders. So if I rewrote this as scientific notation, 5.90 times 10 to the negative second, this still has 3 significant figures, and the zeros that were in place here aren't even part of the way I write this number as a scientific notation, so that makes it even more clear that it's only 3 significant figures. Now challenge yourself to use the 2 simple rules, or well, maybe 3 if you say rule 1 and rule 2a and rule 2b. Challenge yourself to use those rules and determine the number of significant figures in each of the following measurements. And then come back and check your answers. Pause the video and then come back and visit. Alrighty, moving very quickly. 4 significant figures, 6 significant figures, 4 significant figures, 5, 3, 5, 5, 4, 2, 4, 4, 6. Any questions? Let me know and we'll talk about them. Now the rules we've talked about so far are simply for determining the number of significant figures in a measurement that somebody shows you. But what about math? What about addition, subtraction? If I'm going to add 2 masses together, for example, I would get 1.77 grams as an answer. This number only has 3 significant figures. This number has only 2 significant figures. So how many significant figures can my answer have? Well, in terms of addition and subtraction, I look at the decimal. Both of these numbers, both of these measurements go 2 places past the decimal to the hundredths. So that means I can round my answer to the number of decimal places in the measurement that is the least. So I need to round my answer to 2 places. So 1.77 is my answer. If I have a temperature increase from 25.2 to 34.2, 34.2 minus 25.2, subtract those and we get 9.0 degrees Celsius. These both have 3 significant figures, but this one only has 2 significant figures, and that's okay because these 2 values are both in the tenths, so my answer is going to be to the tenths. It won't happen very often in our work in chemistry specifically, but what if I had, just as a side example, what if I had 52.89 plus 103.1? Well, this is 0.99, this is 5, this is 5, so this would be 155.99. Well, if this first number goes 2 places past the decimal, and the second number only goes 1 place past the decimal, so I would need to round my answer 1 place past the decimal. After the 9 is a 9, so I'm going to round up, so I would get 156.0 rounded to the tenths. I don't think this scenario happens very often in measurements because you're often using the same equipment for measurements that you're adding or subtracting. But just in case, I wanted to give you that example. Now, rules for rounding. Some of these rules are going to make sense and some of them are going to challenge your understandings, and I'm okay with that. If you're rounding and the numbers after what you're rounding are less than 5, then they're just dropped. So 24.522, if I'm going to round it to 3 significant figures, that's going to be 24.5, and I'm just going to drop those numbers. 9.0549, after the 5 is a 4. That 4 is less than 5, so they're just going to be dropped, and I'm going to have 9.05. Look, only 1 digit past the number being rounded. So I don't know, when you were like in grade 1, did they say to you, okay, this 9 rounds the 4 up to a 5, and this 5 rounds the 5 up to a 6, and so you get 9.06? I don't know, did your teachers teach you that? Mine did. They were wrong. That's not how scientists do it. Just look 1 place past the decimal. Look at the 4, the numbers get dropped, the answer is 9.05. If the number is greater than 5, you're just going to round up. So after the 5 is a 6, so that means I round up to 24.6. After the 9 is a 7, so I round up to 10, so I get 9.10. That probably sounds exactly like you remember. And now I'm going to challenge what you think. If the number is 5, exactly 5, round to the even number, not up. 5s you shouldn't round up, you should round to the even number if it's 5 exactly. And this might be different than you've ever learned. I will justify, I promise. So 24.55, after the 5 is a 5, and this is a 5 exactly. In other words, there's nothing after the 5, so this is 24.6. 24.45, after the 4 is a 5, but that 5 is a 5 exactly. So I round to the even number, and the even number is 24.4, so I don't round up. So sometimes I round up and sometimes I don't. But what if it's 24.451? This is no longer exactly a 5 after the number I'm rounding. So this is 24.5. Yes, this is different from what you were taught, most likely. Yes, I'm going to justify it. We'll talk about it. So let me try to justify it. Here's an exercise for you. I've got a series of original measurements, and I want you to round up to 3 significant figures the way you were taught, or maybe, yeah, 3 significant figures the way you were taught, and I want you to round to even numbers the way that I just taught you. And then I want you to add the numbers in each of these columns. Pause the video, make it happen. So if you're rounding up, 10.05 becomes 10.1, 10.15 becomes 10.2, but according to my rules, 10.05 becomes 10.0, and 10.15 becomes 10.2, and 10.25 becomes 10.2, 10.35 becomes 10.4, and so on. So fill in the columns if you haven't already, and add them up. Here we go. When I add up these numbers, I get 105. But if I round up, I get 105.5. But if I only round to even, I get 105. You tell me that 105.5 is better than 105, and I'm not sure I'll believe you. So maybe, just maybe, I've convinced you that rounding to even is a logical answer. 5 is exactly in the middle. If it's exactly in the middle, why do we always round up? If you always round up, you create error. So don't round to even. If you round to even, you're rounding up about half the time. And so that it evens out. Yeah, that was a pun. One last thought. To me, this method of rounding 5s is very logical. Hopefully it's logical to you now that you've looked at the previous slide. However, how often in your life as an IB chemistry student are you going to have a number that results in using the round to even rule? How many times are you going to have a measurement where or a series of calculations where your answer is, say, 102.450, and you are rounding at the 4? Well, I would argue that after your calculator, you probably don't just have zeros here, but let's say you did. How often is that going to happen? Probably not very often. Possibly never. So why did I include this? Think about it. We'll talk about it in class. Now let's talk about multiplication and division. I want you to consider a sample of sodium chloride with a mass of 5.00 plus or minus 0.01 grams and a volume of 2.3 plus or minus 0.1 centimeters cubed. Calculate the density. Density is mass over volume. The largest possible value would have a mass of 5.01 grams and a volume of 2.2 centimeters cubed. The smallest possible value for this would have a mass of 4.99 grams and a volume of 2.4 centimeters cubed. Do the math on those calculations and then pause the video and consider kind of where we're going with this discussion. All right, did you do the math? Okay, so 5.01 divided by 2.2, my calculator tells me is 2.77 grams per centimeter cubed. And my calculator tells me that 4.99 divided by 2.4 is 2.079 grams per centimeter cubed. Okay. But what if I just took 5.00 divided by 2.3 using the original numbers that are there? Well, my calculator tells me 2.17. Do you think that 2.277 and 2.079, if we took an average, would be about 2.17? Okay, yeah, probably. Well, this has 3 significant figures. This only has 2 significant figures. So I need to round my answer to 2 significant figures. So I'm going to get 2.2 grams per centimeter cubed. And there is my answer rounded to the proper number of significant figures, which is about in the middle of these 2 numbers, the smallest possible value and the largest possible value based on the uncertainties. So the rules for multiplication and division are: round the answer to match the measurement with the least total number of significant figures. Total number. It's not about the decimal with multiplication and division. Let's look at one last example. What is 4.23 centimeters times 0.0026 centimeters? My calculator tells me it's 0.010998. Well, this number has 3 significant figures. This number has 2 significant figures. So I need to round my answer to have 2 significant figures. And so here I am, rounding it to 0.011 centimeters squared, because that is our unit. So what do I want you to recognize from this? Well, this went 2 places past the decimal. This went 4 past the decimal, but my answer only went 3 past the decimal. Because with multiplication and division, it's not about the decimal. It's about the total number of significant figures in each of my measurements. I used the smaller of those two to determine the number of significant figures in the answer. And there you go. That's significant figures. Thank you for listening. I do appreciate your time. Let me know if you have any questions. Have a great day. See you in class.